Okay. A couple quick little announcements. If you haven't sent me your project, do that today or tomorrow at the latest. Um, Hopefully, everybody here has actually signed into the Pearson MyLab, because if not, I dropped you from the class. So, because I did that on Friday. Your homework, which is a bone of contention with a lot of people. Yes, there's a lot of problems. You only have to do half of them. You can choose whichever half you want to do. I don't care. Okay? So if there's 20 questions, you only have to do 10. All right? If there's 21 questions, you do 11. All right? So pick and choose the ones you want to do. There's a bunch that are the same. Only do one of the ones that are the same. Like, go through and do it so you can hit all the different types of problems that are on there. But you can technically pick and choose what you want to do. Do not worry about your grade on Pearson. That's not the grade you're getting in the class. On the day after when I grade the test, I will put all your grades over in Blackboard. That's the grade you're going to be getting in the class for your homework. So as long as you've done half of it, you will get full credit for that homework assignment. So don't freak out and go, why is my Pearson grade so low? That's why. It doesn't know that's what I'm having you do. So, and there's no way for me to tell it. That's what I'm having you do. The practice test is already up online. So there's a chapter 1 through 3 review test. It's listed as a quiz. It's not a quiz. It's not going to go in as a quiz grade. It's just, it was easier to differentiate it from the homework. You can work on it. I gave you guys 99 attempts at the different assignments, so you can practice it as many times as you want. The test is identical, just different numbers. Okay? So if you can do that test, the review test, you're going to be able to do the test fine. Remember, you're allowed an index card. So as you're going through and doing the review test, if you need to look things up or you need stuff, write it down on the index card. You will be allowed to use StatCrunch and my website for the calculators. So if you want to bring a laptop or something to work with to do your test, that's fine. If you don't, I'm in a room full of computers. You're more than welcome to use one of the computers on the side of the room. Okay? It will be on paper, so you'll have to write down what you did and things like that. So, like when it says do the calculation, say, I use StatCrunch. This is what I did in StatCrunch. Or I use your website, things like that. So this way I know what you were doing to do the calculations. I think that's it. Was there any other questions? Yeah.
When and where is the review test going to be posted?
The review test is already on MyLab in Pearson. Yeah, it's probably all the way at the bottom because they don't sort very well. So yeah, it should already be there. So just scroll down and find it. Next Tuesday's class will be me going over the review test. So if you are great and you already know the test and everything else, and you don't want to be here for the review, you don't have to be here next Tuesday. The test is next Thursday. If you have questions and stuff on the test, come next Tuesday and ask them, because I'm going to go over all 10 questions. Okay, and then that will be posted up on my website with the review and things like that, so you can get that as well. All right, any other questions? Yeah.
And you're saying like the test is basically just going to be these 10 questions?
Yep, those 10 questions, just different numbers.
All right. Thank you.
Yep. Yes. Huh? Oh, you're fine. Okay. No problem. You're fine. All right. Any other questions? Okay. Lots of calculations tonight. We're done with the graphs and things like that. So lots of calculations, lots of formulas we're going to look at today. What are the measures of central tendency? Anybody know? Mean is one. What's another name for mean? Average. Very good. Okay, you've probably done average a lot before, so that's nothing crazy. What are the other ones? Median. And what's the last one? It's another M. Mode. Very good. All right, so mean, median, and mode. That's what we're going to look at to start with. So let's start off with median, or mean, sorry, not median. So there is two formulas they gave you, they're identical. The only difference in these two formulas is the notation. So that symbol right there, that's the little U, that's called mu. It's the Greek letter mu. That's why we use it for mean, because it's mu. You will see that a lot. Whenever you see that, that means mean. It is the population mean, which means that's the mean of the entire population. And then big N is the size of the population. You'll notice the sample mean formula is exactly the same. Not all formulas will be the same when we're looking at a population compared to a sample. So in mean, it is identical. You will see this one right there. That little, it's called X bar. It's an X with a little bar over it. That is what's known as the sample mean. And you'll notice a small little n for the bottom, designating the sample. To calculate mean or average, you add everything up and divide it by how many you have. And that doesn't change for those two. So all you're doing is adding everything up and dividing it by how many you have. Nothing crazy. We didn't add anything new for average. That little symbol right there, that's the summation. That literally just means add everything up. You do not need to memorize these formulas. You're not going to see, like, I'm not going to ask you, what's that formula for mean? And you're going to have to write it down. I'm not going to do that. You have to know how to use it. Okay? So not knowing that, like, making sure you're like, oh, this is the symbol for summation. If you remember, all I have to do is add them all up. You're good. You're fine with that. Okay? The two things that you will need to know, because you're going to see them a lot going forward, is the symbols for mean and sample mean, the mu and the X bar. Those do come up quite a bit. The middle value, also known as median. Median is your middle number. Very, very, very important. And I've had many students not do this. All of your data needs to be in order for you to find the median. Okay, so the very first step you should always do if you're looking for the median is put all your numbers in order. You do not need to do that necessarily for average or mean, and you don't need to do it for mode, although it does make your life easier. For median, you have to. There's two possible situations when we're looking at finding the middle numbers. The first case is if we have an odd number of values. If you have an odd number of values, you can take n plus 1 divided by 2. That'll tell you the spot you're going to look for. So, for example, the one I have there, there's 5 values. So 5 plus 1 is 6, divided by 2 is 3. So I'm going to pick the third value. In that case, it's 5. In the second case, I have an even set of numbers. If you have an even set of numbers, you're going to take the average of the two numbers in the middle, so the median numbers. So again, we're going to take the 6 divided by 2 is 3. I count 3 over from the beginning. That's the 5. I count 3 over from the end. That's the 7. So I take those two numbers, add them up, and divide by 2. And that gives me my mean, or my average, or median. For this problem is 6, because it's the average of the 5 and the 7. I will say average and mean interchangeably the entire time. Just they mean the same thing. Okay. Any questions on finding median? Okay. Remember, I do post all the slides. You have them all. So you don't need to write down every little thing that's on the board. We'll be here forever. All right. Okay. The next one we're going to look at is mode. I'm going. Mode. Mode is the one that appears most often. So this is the mode. This is the only one that will work for qualitative data. Okay, so median and mean you cannot use for qualitative data. You have to be able to do calculations with them. So they have to be quantitative data. Mode does not. Mode you can do with qualitative data. You're looking for the one that appears most often. Mode also has some different options to it. So I can have one mode, just one number appears most often. I can have multiple modes. They have bimodal here, but you can have 3, 4. You can have multiple modes. So anytime more than one number appears at the exact same amount, that would be a multimodal situation, and you list them all. I also could have no mode, where they all appear the exact same number of times. So if every single number comes up once, I don't have a mode. If every number comes up twice, I don't have a mode. Okay? So it is not always necessarily the one that like appears more than once. So if every number appeared twice except for one number showed up once, every other one's a mode except for that one number actually, which is annoying, but it doesn't happen very often. So just remember for mode, you can have multiple of them. All right? Yeah. Bimodal is just 2. Multimodal means you can have more than 2. Like you can have 3 or 4 modes. That's possible. They just didn't write them all in there. And I didn't write the actual topic, multimodal. All right. Let's look at one. That is really small. Come here. I want. It's not going to be doing. Fine. Do it myself. All right. So here's my numbers. I'm being nice. I put them in order for you. All right, so when we're looking at these, I have 12 of them. So this is even. Mean is pretty simple, just add them up. So on my website, I actually have this little calculator right here. It looks just like this. You can type in whatever numbers you want here. So like if I added a number here, it'll automatically change these. So this is on there. You can easily use this to find your mean, median, and mode. So you do not have to sit there and type all the numbers into your calculator and do the division and everything else. Because 99% of mistakes, you know exactly what you're doing. It's because you typed the number wrong, not that you didn't have any clue what you were doing. So this takes care of that problem. All right, so we add them all up and divide. We got 59.25. Your mean does not have to be one of your numbers. Okay? So, but it should make sense with your data. Okay, so if we look at all these numbers, we're going from 22 to 96. 59 sounds about the middle. Sounds right in the middle there. Okay, that would kind of make sense. But let's say I added a number, I added 99, but let's add 999,000. Or 9,999. Now you notice my mean is really high. Okay? And we look at it and go, okay, did I screw something up? Well, yes. I probably shouldn't have had the 99.99. I probably should have put a comma between those. Or, no, I didn't screw anything up. That number really was there. That's why my mean's so high. Okay? So when you get a number that looks wrong, take a second look at it. Make sure you didn't make a mistake. Or if it really is just a number that's way out there. We're going to talk about outliers next class. So 9,999 would be an outlier in this situation. That's why the mean is so much higher. Median. I have 12 numbers. So what's the number I'm going to use for my median? So 12 would be 6. 12 divided by 2 is 6, right? So I'm going to count 6 over and 6 the other direction. So yeah, 6, 7. 2, 3, 4, 5, 6. So 6 and 7. All right, so we've got those two numbers. Add them up, divide by 2, and I get 61. Again, a lot. If it's odd, your median will be in the actual values there, but since it's even, your median does not necessarily have to be one of your numbers either. It's between those two numbers, and that's okay. The median should absolutely make sense. You should be able to look at your data and go, yeah, that's probably the middle of the data. Okay. Mode. In this set of numbers, we're looking at the ones that appear most often. In this case, there's only one. The 266 is right there. But if we go back and look at the one I just did over here when I added the 299s, you'll notice my mode is now 66 and 99. Okay, so we can have multiple modes in there. And if I was to add another 99 in here, you'll notice the 66 goes away. Okay. And if I was to add another 28 in here, you'll notice I have 3 modes. Totally fine. And if I took away a 66, you'll notice I have no modes. So all those are valid answers. So the mode does not necessarily only have to have one. I will tell you that is the hardest thing for a calculator to do. Mean and median, calculators can calculate really easily. Mode is not something that a calculator can always do. Calculators are designed to give you one answer. And since modes can have multiple answers, it's very hard for a calculator to do those things. Okay? So like your TI calculators and stuff like that, a lot of times they'll get mode wrong. All right, any questions with mean, mode, and median? I'm hoping for the vast majority of you, you've heard of those before. Most times in high school, they cover at least mean, mode, and median. So that's normally the extent of your stats training. All right. So there's something known as resistance to extreme values, or where it skews things. And if you remember, we were talking last class about skewed to the left or skewed to the right, and we said the tail is what pulls it. The tail is your outliers. The tail is the things that pulls things, because that's what's going to pull your mean in that direction. So if I have a skewed to the left, that means my mean is less than my median. That means I have some values that are really small that is pulling my mean in that direction. Symmetric, mean and median should be about the same. All right? So if the data is about symmetric, your mean and median should be about the same. They don't have to be exactly the same, just close. So like, I will come back to this slide in 1 second. I will come back, don't worry. So like in this one, my mean is 39, my median is 22. That's not quite close enough. So this data would be skewed to the right because my mean is bigger than my median. Okay? I'm going to go back, don't worry. All right, so as we saw in that one, I said my mean was bigger than my median, so it was skewed to the right. In the other data, if I remember right, my mean was 59 and my mode was 60 or 61. Those are about the same. So I would say that data is probably pretty symmetric. And let's say I have, I'm living in Greenwich and I have a bunch of $1 million homes. However, somebody decides to put in an apartment building and list all the apartments for $100,000. That would pull the mean a lot lower. So that would skew it to the left. Okay. Mean gets moved. So outliers will move that mean. Median does not. Right? Median is resistant to movement. So if I added a number on one end of it, or if I change the number, the median doesn't necessarily change, where mean does. Any number that changes is going to change that mean. Good. All right. Here's 6 bolts. 10.2, 10.1, 10.3, 10.2, 10.2, and 50.5. We want to find the mean and the median of these. Totally cheating, I know. But that's why I wrote this. It would help if I clicked the other button. There we go. All right, so we've got our numbers in there. We had 6 numbers. My mean is 16.92. My median is 10.2, and I have a mode of 10.2. Which of those 3 things would be the best measure or the best representation that represents a typical bolt weight? Should I use mean or median? You'll never want to use mode for this. So should I use mean or median for this? Okay, why? Yeah. So that 50.5 is doing what to my data? It's skewing it right. It's pulling my mean higher. Okay. This is why most times, if you're looking at home prices, salaries, or anything else like that, they always label the median value of those. They don't give you the average or the mean. They always say median because there's always those outliers that will pull it in one direction or the other. Okay. So in this case, that 50.5 is an outlier. It's pulling my data in one direction. So I would want to use median. All right. Any questions on mean, mode, and median before I move on to the stuff that you might not have seen before? Okay. Range. So now we're going to move in. So we looked at the measures of central tendency. We are now going to look at measures of dispersion. So we're looking at how spread data is. Okay. So the first one that we're looking at is what's known as range. Range takes the largest value minus the smallest value. It is not resistant to outliers because the largest value or the smallest value might be extremely small or extremely large. Okay, notice it doesn't say cut out the outliers. Range is literally just the largest minus the smallest. You also need to have your data in order to do this. All right. Probably after the symbols that we talked about, this is probably the most important formula you're ever going to see in statistics. Don't worry, I'm never going to have you actually physically do this out by hand. The stat teacher last semester did, and I thought he was nuts. I would never do this out by hand. It is a long process to do this. However, I do want to explain what this is. So this is the formula for standard deviation. The pieces that you absolutely do need to know are, again, the symbols. So we have baby sigma. So that is the Greek letter, and that one is for standard deviation. And then we have the sample standard deviation, which is the little s. You will notice that these formulas are slightly different. This one has the n on the bottom. This one has n minus 1. So when you're doing the calculations for standard deviation, it is important to know which one you're going to use. Are you using a sample, or do you have a population? Because that is going to change your answer slightly. Okay. So what standard deviation does is it's basically figuring out the average distance between the mean and that value. Do I have one that I can quickly use? Let's see if they give me a quick little table. They don't. Might be able to do this in StatCrunch. Probably should have figured that out before, but that's okay. I will do it up by hand. All right, so I'm just going to make up a couple values here so you can see what they are, and then we're going to do the calculation so you can see how this works. So I've got 82, 77, 90, and 71. All right. Let me quickly add those up and divide by 2 or 4. Okay, 80. All right, so my average, or my mean, is 80. So, to find standard deviation, the reason I'm showing you this is so you understand what standard deviation is, not that you're going to do this, because you're going to see how long this process is. If I'm going to look for distance, I want to find out how far away something is. So I'm going to do 82 minus 80, 77 minus 80, 90 minus 80, and 71 minus 80. So I get 2, negative 3, 10, and negative 9. So that's the distance. Then we square them all. So 4, 9, 181. Then I add them all up. $194. And then I divide by how many I have. And then I take the square root of that. And that's my standard deviation. Now imagine doing that for 100 numbers. Or even 20. It takes a while to do it for 4, let alone a ton. So what that's doing is it's basically telling me how spread the data is. So it's giving me an average of how far away the actual values I have are from the middle value. Okay? So what I've given you is the ability to do it on a calculator. So what this is going to do, actually use similar numbers. So those are the 4 numbers that I originally did. And you can see there's 2 numbers here on either one. So this is the population, and this is sample. It also gives you what's known as variance. Variance is exactly the same as standard deviation, except it's squared. So it's the number I got before I did the square root, the 48.5. You could be asked for either of those numbers. They're both valid. Standard deviation is just the one we've standardized around using. Okay? Because it's a little smaller, takes care of a lot of little issues. You will notice that the standard deviation for the sample will always be bigger than the standard deviation for the population. Why? Why do you think that's the case? What's a sample? Is it smaller than the population or bigger than the population? Smaller, because it's a piece of the population, right? So would that be more accurate or less accurate? The sample. Less accurate, right? Because if I want the most accurate, I'm going to use the population. So your samples are going to be a little less accurate. And that's why we have that n-1 in there, is to show that it's not as accurate of information. So it gives us a little bit more variation in our data. Okay? Because if you pick the sample of 10 numbers and you pick the sample of 10 numbers, you might get 2 totally different standard deviations. They're going to be close, but they're not going to be exactly the same. And neither one of them is probably going to be the exact same as the population. Okay? So by having that, that gives us that little variety in there. That's what the n-1 helps us with. Okay? What was my next slide? All right. Back to the formulas if you haven't written down the formulas. It is more important for you to know how to use a standard deviation and what it means than to be able to calculate the formula. One of the things that we're going to be looking at to compare things and to figure things out is we need to know that standard deviation. We need to know how varied the data is. Because, like, for example, I'm going to switch slides. This one, let's do those 4 numbers again. Those are the 4 numbers. What if I added 100 in here? Okay, so notice I added another bigger number. My standard deviation changed. It went up. If I added a 900 in there, it goes up even more, right? What if I balanced it out and I put a 1? So, like, if I did 100 on one side and a 1 on the other side, that should balance it out, right? But it doesn't. Because those values are so far away from what the mean value is in the problem that it's a lot more varied. That variance is higher. Okay? So, is your standard deviation resistant to outliers or not? It's not. Okay, so when we're looking at that resistance, standard deviations is not resistant. Okay? It will move based on those higher numbers. It will increase. Okay? See, 100 doesn't change it that much because my mean was at 84. It's not that big of a deal. But when I put numbers that are really, really low or really, really high, I can start getting that very high variance. And the reason why, if we look back at the formula, what's the very first step in the formula? It's taking that number away from the mean. So if I have a really, really big number here, my square root's going to be high. Every other number is going to be high. That's why my standard deviation is high. Okay. That's why I show you this, more so you can understand how the numbers move in the equation, not that you're going to do it. All right. Standard deviation. This is where standard deviation is used. So, anybody here in the trades? Carpentry, electrical, plumbing, anything like that? Good. How tall is the door? Huh? No. It's lower than that. Anybody have a guess other than 8 feet? Because I got one guess. Anybody else have a guess? Okay. Are all doors the exact same height? Should all doors be the same height? See, we live in New England. If I ask this question in Arizona or out west, the answer would be yes, all doors are the same height. See, we live in New England where houses were built hundreds of years ago. So doors are not always the same height. The standard for a door height right now is 80 inches. Why? Anybody have a guess? Yeah. Huh? Okay. So would the average height of the American be 80 inches? It'd be less than that, right? But we're going to use something with average. We're going to use something with that. So the average height of a male in the United States is about 70 inches. So 5'10". Okay? With a standard deviation of 3 inches. That means, and that's what this empirical rule says, 68% of all men, I would do this for women too, but there's a reason I'm using that. Because we're a little taller, and that's what happens with doors. So 68% of all the men are between 5'7" and 6'1". So 57 inches to, or no, 67 inches to 73 inches. 95% are within 2 standard deviations of that mean. So 95% of all men are between 54 or 64 inches and 76 inches. Okay? And the 99.7 are within 3 standard deviations, which means between 51 and 79 inches. What did I say the height of the door was? 80. So with that height, more than 99.7% of all people would be able to fit through that door without bopping their head. Okay? And since women on average are shorter, even more women would be able to pass through the door. Okay? So that's where that number came from. So why don't do it 85 inches? Make it even better. Cost money. If I had to do it 85 inches, doors would cost more money. They're more material. Okay? So when you're looking at the design of buildings and houses and stuff like that, standard deviation goes into the play of how they're done. All right? That's why, if we look back at houses in New England when they're 100 years old or more, we were shorter. We've gotten taller over the years. We've gotten wider over the years. That's why if you go into some of these old houses, the doors are shorter, smaller, and shorter. And your steps are taller because they didn't have enough room in the house to put the steps. Okay? So there's a lot of design choices that were back then were the same then. They have standards that they followed. It's just we've grown. So our standards have to change slightly for that. Okay? So I said that with 3 standard deviations, right? We have 99.73, so everything. But do I really care about the people on the low end with this door? No. So if I eliminated that, I'd have basically 1 out of every 1,000 people would hit their head going in and out of the door. And that's just the male population. If we included the women's side to it too, it'd be probably 1 out of close to 5,000 people would actually hit their door going out the door. So, do we need to design something that would worry about a 1 in 5,000 chance? No. So, if you're in that situation, you'll learn to duck a lot. Okay? All right. So, anybody ever get in an elevator and see the sign inside of an elevator? Yeah. What's the weight? Yeah. No, it's a lot higher than 325. 325, I would destroy the elevator, which would probably not be a good thing, which is one reason I don't go into elevators. Been stuck in one too many times. All right. 2,000 actually. And then it says, or 10 people. So they're assuming the average weight's 200 pounds. What are we getting as Americans? We're getting heavier. Okay? So that 2,000 or the 10 people doesn't work much anymore, which is why a lot of new elevators, their signs just say 2,000 pounds. There was actually a situation in New York where there was a party boat that went out. Now, boats have capacity limits and weight limits. Okay? Now, they didn't then. They had the capacity limit. And this party boat was rated for a capacity of 30 people. So this law firm went out and booked it for their employees. And their employees were mostly male and mostly overweight. And they had 30 people. When they got in the boat capsized after a little while. Because, yes, they were at the capacity or under the capacity, but they were way over the weight for it. Because on average, those men were heavier than what they would have considered the capacity limit. Because when they created the capacity limit, they created it assuming a normal mix in population. Or in the way we're looking at it, a sample, a normal mix in sample. However, their sample was way off on one end. And that caused a problem. So this is how, when we're looking at statistics and we're looking at standard deviation, why that unit is so important. Because it allows us to take a single number and determine where people are going to fall. And where I need to build things to make sure that the majority of things are covered. And that I don't need to worry about the extreme outliers there. Okay. What's this curve here called? That is the bell curve. And I said we're going to use it a lot. This graph is what? Is it skewed left, skewed right, or symmetric? This is symmetric. Okay? So standard deviation, the empirical rule that we were just talking about, assumes that the graph is a bell curve and symmetric. Okay? So this empirical rule that we're looking right here assumes that. The vast majority of situations when you get enough data will fall into a nice bell curve. This is why this is the one we use most often. However, there are situations where it is not a nice bell curve. And that's where we have Chebyshev's rule. Chebyshev's inequality works on any distribution, even if it is skewed. But what it tells me is it doesn't tell me the exact value like the empirical rule does. Because believe it or not, the empirical rule actually uses calculus to calculate the actual average under the curve. So because we have that formula to create the curve, we can do that. Chebyshev's works for everything. So we don't have an exact value. But what we do have is we can figure out at least. So his rule says, if you plugged in 2 for this, you get 1 minus 1 over 4, which is 0.75. So you get 75%. So it says 2 standard deviations away from the mean, you'll have at least 75% of the data. 3 standard deviations, you'll have at least 88.9% of the data. So you will always have an at least value. It is not going to give you the exact, unlike we were just doing, but it will give you at least. And for those, I do have a calculator for Chebyshev's rule too. Nope, that's not what I want. That is not going to help me. I need to fix this calculator, make this a little better. So where you're going to see this problem on your homework and stuff is a problem like this. So IQ, the mean IQ is 100. And the standard deviation for it is, where is it? 16.1. Is the standard deviation. So they want to know, so one of the questions wants to know what percentage of people are between 67.8 to 132.2. They want to know what percentage of people are between those. So what you need to do, and you can use this visualizer to do it, but what you need to do is you need to figure out how many standard deviations away they are. Okay? So how many times do I need to add 16.1 to 100 to get to 132.2? It's plus 2. To go down to this, it's minus 2. So we could take this and go down to minus 2 and up to 2, and there's my answer. And since it's 2 standard deviations, you don't even need to do that. 2 standard deviations is 95%. This will help you if, say, it was 1 on the other end and 2 on this end. It'll actually break those up for you. So say instead of going down to 67.8, I went down to 83.9. So that's only minus 1 down. So between 83.9 and 132.2, there's about 82% of all the people. And if you went 1 more, you'd be at 148.3. So 3 standard deviations gives you an IQ score of 148 approximately. That means that if you claim you're above 148 on the IQ scale, that means you are better than, was it 99.87 people? So, like I said, 1 out of 1,000. And I'd be willing to bet if you went through and asked anybody, like just asked average people, like, what's your IQ? They're all going to say well over 100. Okay. And based on the data, that's not really true. Most people are between 83.9 and 116.1. Almost 68%, almost 70% of the people are between those two numbers. Okay? That's average. That's what standard deviation and bell curve does. All right. Any questions? Let's do that. I might. Hold on 1 second. I want to see. Yeah, I can cover that on Thursday. All right. Any other questions with the measures of central tendency and the measures of variance? Okay, that's 3.1 and 3.2. So you should be up through 3.2 in your homework. And remember, you only have to do half the questions. And on your test, you'll be allowed to use a computer to do the calculations. You can use my website. You can use StatCrunch. You can use Desmos. Okay? All right. I will see you on Thursday.